Hello, today we are going to talk about linear models in machine learning. So, linear models are a class of models that are widely used in practice. They make predictions using linear functions of input features. Linear models for regression. For regression, the general prediction formula for a regression looks like in this way, and where W0, X0 up to so on WP, XP plus a term that is called as a bias, where X0 to XP denotes the features uh, of a single data point, and W and B are the parameters of the model that are learned during the training process. And Y hat is the prediction model, is the prediction that the model makes. For a dataset with single features, this is the above equation reduces down to this y cap is equal to w0 x0 multiplied by x0 plus b. This is the expression that reduces down for a single feature, which might remember from high school mathematics as equation of a line. So w0 is the slope and b is the y offset or intercept. For more features, W contains the slopes along each feature axis. When there are more than one features, then W contains the more than one slopes. Alternatively, we can think of the predicted response as being weighted sum of input features. So we can think of predicted response as being a weighted sum of input features with weights given by entries of W. Trying to learn the parameters W is equal to W0 and B as one-dimensional wave dataset might lead to the following line. So what we are going to install, first we install the mglearn library, and then we import the mglearn and plot some data points for wave regression dataset. And the plots look like this way. We add a coordinate cross. This is coordinate cross, and we add it, and and then we draw the plot for the plot, and then we draw a line passing through these points. Looking at w is equal to 0, we see that slope is around zero point 0.4 for this line. And the intercept is where the prediction line cross the y-axis. This is slightly below 0. So which we can also confirm in this image. So linear models for regression can be categorized as regression models for which the prediction is a line for a single feature. Prediction is a line for a single feature. Um, uh, Prediction is a line when there is a single feature, and prediction or classification or prediction model is a plane when there are two features, and the prediction model is a hyperplane when there is a high dimensional features. If we compare the predictions, if you compare the predictions made by the straight line with those made by k nearest neighbor in our previous example, using a straight line to make predictions seems very restrictive. It looks like all the fine details of the data are lost. In a sense that this is true, it is a strong assumption that our target y is a linear combination of features. We assume that our target y is a linear combination of features. This is a linear combination of features. So by looking at one-dimensional data gives a somewhat skewed perspective. For dataset with many features, linear model can be powerful. In particular, if you have more features than training data points, any target y can perfectly model as a linear function. In particular, if you have more features than training data points, any target y can perfectly model as a linear function. There are many different linear models for regression. The difference between these models lies in how model parameters W and B are learned from the training data, how we learn the parameters W weight and bias from the training data, how model complexity can be controlled. We will now take a look at how most popular linear models for regression they work. And first of all, we look for the linear regression model, a kind of ordinary least squares. Linear regression or ordinary least square is the simplest and most classic linear method for regression. Linear regression finds the parameters w and b that minimize the mean squared error between predictions and the true regression on y on the training dataset. The mean squared error is the sum of squared difference between the predictions and the true values. The mean squared error is the sum of squared differences between predictions and the true values. Linear regression has no parameters, uh, which is a benefit, but also has no way to control the complexity. We can't control the complexity, or we can't control the parameters using the linear regression model. But it has no way to control. Here is the code that produces the model you can see in previous figure. So what we do is that we uh, uh, from sklearn, we take the linear model, and import the linear regression, and then we make the model selection and split into training testing dataset. Then from mglearn dataset, we make a wave dataset of 60 points and split it into training set and test set. X train, X test, Y train, Y test. And then we uh, apply the linear regression on the training dataset. And it works like that. This way, the slope parameter W, also called weights or coefficients, are stored in the coefficient attribute, while the offset, intercept, or P is stored in the intercept attribute. Slopes are stored in the coefficient attribute, while the offsets, they are stored in the intercept attribute. So we are going to see, because we have we only one features. So this there is the corresponding coefficients, the slope, and corresponding intercept y. The intercept attribute is always a single floating point, while the coefficient attribute is a numpy array with one entry per input features. As we can see that we have only single input features in the wave dataset. Linear coefficient has a single entry. In our case, linear coefficient has only one entry, but in fact, this linear coefficient, it could have a array. It could be an array when there are more than one features. Let's look at the training set and test set performance. So in this case, we are going to check the performance for the training set and the test set. So when we run that, this is the training set and test set performance. R2 score that is used for metric for regression is around 66% and is not very good, but we can see that the scores for the training and test are very close together. Training set score and the test set score, they are very close to each other. This means that we are likely to underfitting, because when training and testing, they are very close, and that it may seem that there is an underfitting. For this one dimensional data set, there is a little danger of overfitting, as the model is very simple. The model could be overfitting, subject to the overfitting. However, higher dimensional data set, linear models become very powerful. When we have the higher dimensional data set, then the linear models, they become very powerful, and there is a higher chance of overfitting when we have a higher dimensional data set. Let's take a look at how linear regression performs on a more complex dataset like Boston housing dataset. Remember that this dataset is 506 samples. It has 506 samples, and each sample has 105 derived features. First, we load the dataset and split it into training and test set. Then we build the linear regression model as follows. So first we download the dataset from mglearn library, and then split it into training and test, and use the linear regression to fit the training dataset and test dataset. So I run this code, and now we see that when comparing training and test scores, we find that we predict accurately on the training set, but R2 on the test set is much worse. So I check and the performance on the training set and the test set, and see that training set performance is very good, 95%, while set the testing performance is very low. This discrepancy between performance on the training set and test set is clear sign of overfitting, that the model it tries to fit the training set. Therefore, we should try to find a model that allows to control the complexity. We should use the model that controls the complexity. One of the most commonly used alternative to standard linear regression. Alternative to standard linear regression is the ridge regression. We are going to explore the ridge regression. Uh, Ridge regression is also a linear model for regression. So the formula it uses to make prediction is the same used for ordinary least square error. In a rig regression, the coefficients are chosen not only so that they predict well on the training data, but also fit on the additional constraints. And not it predicts well on the training data, but also performs well on the additional constraints. We also want the magnitude of coefficients to be small as possible. We want the coefficients to be small. In other words, all entries of W should be close to zero. Intuitively, this means each feature should have as little effect on the outcome as possible. Each feature should have little effect on the outcome as possible. The constraint is an example of what is called regularization. Regularization means explicitly restricting a model to avoid overfitting. What is regularization? Regularization is explicitly restricting the model to avoid overfitting. The particular kind used by ridge regression is known as R2 regression. This particular kind of ridge regression is R2 regression. Ridge regression is implemented in a linear model dot ridge using the linear model dot ridge function in the library. Let's see how well this it does on the extended Boston housing dataset. So sklearn dot linear underscore model import ridge. So this is the ridge uh, function we are calling, and we are going to fit it on the training and test set and check the performance on the training set and the test set. So I run this part of the code and see that the training set performance is 89%, while set the testing set performance is 75%. As you can see, the training set score is lower than the linear regression. For linear regression, the training set score was 95% when using the linear regression, and is lower than the training set score of ridge is lower than linear regression, while the test set score is higher, but the test set score of the ridge regression is higher than the linear regression. Linear regression was 61% test score, but the ridge regression test set score is 75%. This is consistent with our expectation. With linear regression, we are overfitting the data. Ridge is more restricted model, so we are less likely to overfit. Uh, Rich regression is more restricted, and we can avoid the overfitting. A less complex model means decreased performance on the training set. A model that is less complex, it means it will drop down the performance on the training set, but it will better generalize, means the performance will be better on the test set. As we are interested in generalization performance, we should choose the ridge model over the linear regression model so that the performance is reasonable on the test set as well. The ridge model makes a trade-off between the simplicity of the model and its performance on the training set. How much the model places on simplicity versus the training performance can be specified by using the alpha parameter, that how much simplicity we should introduce. In the previous example, we used the default parameter of alpha is equal to 1. There is no reason why this given us the best trade-off, though. The optimum setting of alpha depends upon the particular data set, that what should be the value of the alpha, how much should be the complexity and how much should be the generalization. We are increasing alpha forces the coefficients to move towards zero. When we increase the alpha, it forces the coefficients to go towards zero, which decreases the training performance but might help better generalization. So increasing alpha forces the coefficients to move towards zero, and it decreases the performance but better generalization. So here we are going to run this part of the code, and we see that now the alpha has changed to 10. Before it was the default value of alpha is equal to, here the default value of alpha, and it was equal to 1, and now here the default, and we have changed the value of alpha to 10, and we see that how the performance is. We see that the training set performance is 79% and test set is 64%. Decreasing alpha allows the coefficient to be less restricted. So when we decrease the coefficient, then the coefficient become less restricted. For very small values of alpha, coefficients are barely restricted to at all, and we end up with a model that resembles the linear regression. Now we have changed the alpha to zero point 0.1, and we see that the training set performance is high and test set performance is low. Alpha is equal to 1 seems to be working well. We could try decreasing alpha even more to improve generalization. We could try decreasing alpha. We keep on decreasing alpha and see that even more to improve, and see that about the generalization. We can also get a more quantitative insight into how the alpha parameter changes the model by inspecting the coefficient attribute of the models with different values of alpha. A higher alpha means a more restricted model. So we expect the entries of coefficient to have smaller magnitude of high value of alpha than the low value of alpha. This is confirmed in the plot in the figure. Comparing coefficient magnitudes for ridge regression with different values of alpha and regression. For different value of alpha, we check the ridge plot. I run this part of code and see that for different values of alpha, how the ridge plot looks like. For alpha is equal to 1, alpha is equal to 10, and alpha is equal to 0.1. Here, the x-axis enumerates the entries of coefficient x is equal to 0, shows the coefficient associated with the first feature x is equal to, and x is equal to 1, the coefficients associated with the second feature, and x is equal to 100 is the coefficient associated with the 100th feature. The y-axis shows the numerical values of corresponding coefficients, numerical value of corresponding coefficient. The main takeaway is here is for alpha is equal to 10. We make the alpha is equal to 10. The coefficients are mostly between -3 to 3. When alpha is equal to 10, the coefficients are -3 to +3. The coefficients of ridge model with alpha is equal to 1 are somewhat larger. Now we put the alpha is equal to 1, and now the coefficients range, it is larger from maybe -9 to maybe 15 or 18. And the dots correspond to alpha is equal to 0.1. Now alpha is equal to 0.1, this green one. The larger magnitude still, and there is a very large magnitude. And many of the dots corresponds to linear regression without any regularization. And it means there is no regularization, and it seems that alpha is equal to 0. They are large enough that they are outside of the chart. Some of the points are outside of the chart. Another way to understand the influence of regularization is to fix the value of alpha, but vary the amount of training data available. But the other point of observation is we keep the alpha fixed and change the amount of training data. For figure below, we subsample the Boston housing data set and evaluate the linear regression and ridge regression on subsets of increasing size. So we run this part of the code. So here we see that the blue lines are using the rich regression, and the yellow lines are for the linear regression. So as one would expect, the training score is higher than the test score for all data set sizes for both rich and linear regression, because rich is regularized. The training score of rich is lower than the training score of linear regression across the board. The training score of rich, this is the training score of the rich is lower than the training score of the linear regression. However, the test score of the rich, this is the test score of the rich, is higher than the test score of the linear regression. For less than 400 points, linear regression is not able to learn anything. Less than 400 points, linear regression cannot learn anything. As more and more data become available to the model, both models improve. As more data comes in, the both model, linear model and the rich model, they learn well. Uh, and they improve, and linear regression catches up. Linear regression, it catches up the linear regression catches up the ridge regression. In the end, you can see that the performance of the linear regression and the ridge regression, it is become the same. So the lesson here is that with enough training data, regularization becomes important. When we have the enough data, the regularization becomes less important. Sorry, the regularization becomes less important. And given data, enough data, rich and linear regression, they have the same performance. Another interesting aspect is the decrease in training performance for another interesting aspect is the decrease in the training performance for linear regression. If more data is added, it becomes harder for a model to overfit and memorize the data. When more data comes in, it becomes harder for the model to overfit and to memorize the data. Then it comes the third regression model, that is the Lasso. An alternative to rich for regularization, for regularizing linear regression, is the Lasso. With rich regression, using the Lasso also restricts the coefficients to become close to zero, but in a slightly different way. We call L1 regularization. We call this as L1 regularization. The concept of L1 regularization is that when using lasso, some coefficients are exactly zero. This means features are entirely ignored by the model. This can be seen as a form of automatic feature selection. Mm, Having some coefficients be exactly zero often makes a model easier to interpret and can reveal the most important features of our model. So we apply the lasso to extended Boston dataset. We import the lasso from the sklearn linear models, uh, import the NumPy, and we apply the lasso model on the training data and the test data, and we check the performance. For training set, the performance is 29%, and test set performance is 4%, and we are using the four features. As you can see, the lasso does quite badly both on the training and test set. This indicates that we are underfitting, and we find that it used only 4 of the 105 features. Similar to Ridge, Lasso also has a regularization parameter that controls how strongly coefficients are pushed towards zero. In previous example, we used the default value of alpha 1. To reduce underfitting, we try decreasing alpha. We avoid the underfitting and we decrease down the alpha. When we do this, we also need to increase the default setting of max iteration. Now we also change the default setting of the max iteration. Now we change the lasso alpha to 0.01, and maximum iteration, we also change that. And then we train this model and learn it, and see that the training set accuracy goes to 90%, and test set accuracy, it goes to 77%. And now the lasso model is using 33 features. Now it is using the 33 features. A lower alpha allows us to fit a more complex model. That when we decrease down the alpha, we have made the Lasso model more complex, which worked well or better on the training and the test data. This performance is slightly better than the rich, as we are using 33 of the 105 features. This makes the model potentially easier to understand. If we set alpha too low, however, we again remove the effect of regularization and end up overfitting, using a similar to linear regression. Now we change the alpha to very small value and we run it, and we see that the training set accuracy is 95% and test set accuracy is 64%. And now it has automatically used the uh, 96 features. Initially, this Lasso was using only 4 features, and when it was using 4 features, it was causing the underfitting. Then we changed the alpha parameter to zero point 0.1, and then it was a better performance and better generalization, and the training set accuracy raised to 90% and test set accuracy raised to 77%. With the feature number of features that it used was 33. Then we move a step further and increase the alpha value to 0.0001, and then the training set accuracy increased 95%, but test set accuracy it decreased down to 64%. And this time the Lasso model was using 96 features. So again, and now it is causing the overfitting because the performance is better on training but decreases on the test set. Again, we can plot the coefficients of different models. The result is shown in the figure below. Comparing coefficient magnitude for Lasso with different values of alpha and ridge. So for different values of alpha and ridge, we make a plot, and we say that Lasso is 1, it's a blue line, and Lasso is equal to 0.01 is the brown lines or yellow lines, and Lasso is equal to 0.0001 is the green one, and rich alpha is equal to zero point 0.1. So this is the other red one, comparing to the comparing the ridge and the Lasso. For alpha is equal to 1, for alpha is equal to 1, we not only see the most of the coefficients are 0, most of the coefficients are 0, but the remaining coefficients are also small in magnitude. Decreasing alpha to 0.01. Now we decrease down the alpha to 0.01. We obtain the solution as shown in the orange dots, which obtain the solution as orange dots, which causes most features to be exactly 0. Using alpha is equal to 0.00001, 0.00001. Okay, maybe it is 0001. We get a model that is quite unregularized and with most coefficients non-zero and large magnitude. For comparison, the best ridge solution is ridge model with the 0.1 has similar predictive performance of Lasso model with the with the 0.1, but using the ridge all coefficients are non-zero. Using the ridge all coefficients are non-zero, but using the Lasso some of the coefficients are 0. In practice, ridge is usually the first choice between two models. However, if you have a large amount of features and expected only a few of them to be important, Lasso might be a good choice. Uh, Similarly, if you would like to have a model that is easy to interpret, Lasso will provide a model that is easier to understand, as it will select only a subset of input features. What is the benefit of the Lasso model? If you have the many features, it selects the better features from those number of features. So this is the advantage. While said the reach or the linear regression, it selects all the features in the model. So what the Lasso does a kind of feature engineering, feature selection inherently by changing the value of alpha parameter. So scikit-learn also provides the elastic net class, which combines the penalties of Lasso and Ridge. In practice, this combination works best, though at the price of having two parameters to adjust, one for L1 regularization and one for L2 regularization. Next, we will talk about the linear models for classification, logistic regression, and linear SVM. See you.